Today I'm going to talk about data, something that is kind of a large topic, but I'm going to talk about data. That is what this talk is primarily about. And it's also about Postgres, it's also about space, it's also about Saturn. Perfect thing for an afternoon conference talk, I think. Some patience is going to be required on your part. So what I want to discuss is the process that I went through creating a book. I just wrote a book, and it was my process of discovery as I dug through the data from the Cassini mission to put together this book. And I started out with the idea that I wanted to do something about Postgres, and I started out with the idea was I'm just going to do e-commerce, and I'm going to build out a shopping cart and whatnot. And then I thought, that's boring. It's just been done so many times. So let's use some data from space. And that's what I did. It's about sleuthing and diving in, structuring data, normalizing things, and building up an interesting database. This is the book, by the way. I just published it about 2 weeks ago. It's just on my website. I'll talk more about that later on. I was inspired by The Martian to write this book. And this quote from Andy Weir is one that I really, really like. And he talks about his writing process when he put together the book. And what he did was he let science drive the plot. And I thought that was really interesting because he'd solve one problem in the book and move on. And I thought, well, I could probably do the same thing with the data from the Cassini mission. Because my idea was I just wanted to, take the data that I could find from Cassini and just load it into the database and let's go. But the programmer in me is like, well, no, let's structure it in a linear fashion. We'll build our narrative and blah, 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 blah. And that was just not possible with the amount of data that I had. So I thought, well, all right, let's just load the data up and we'll let the data tell me what the story is. So before we get going, who has heard of the little moon Enceladus? Anybody in here? Okay, good. We've got 2, 3, 4, 5. Okay, well, when I started looking through the data, I just thought, well, what's the Cassini mission all about? Let's find some interesting things. And Enceladus was about the second or third thing that I looked at. And it blew my mind. I couldn't believe that this little moon was not on the front page of every science magazine constantly. It turns out that this thing is spewing water ice into space. That's what's happening there in the southern pole of the planet, or the moon. Spewing water ice and a bunch of other stuff into space. And the discovery of all this from the Cassini probe basically turned planetary data science on its head. Everything that they thought they knew about planets and the way planets work and the way they're formed completely went upside down. By the time the Cassini mission was done, this little moon right here was the leading candidate for life, alien life outside of the Earth. And I found all of this out as I was just doing some investigations behind the data, just kind of reading online, seeing what I could find. And it all started back in the 1980s when Voyager went by Saturn, and it was just snapping some pictures. And it's a fun little trivia story. I'm going to get to the database stuff. I promise. It's coming. Just got to build this up. You guys got to be patient. Anyway, so Voyager was cruising by Saturn, and it was taking some pictures, and it had the camera mounted on this arm, and it could move the camera anywhere without having to change the rotation of the spacecraft. Cassini was not that way. Cassini's cameras were hard-mounted, but back in the 1980s, Voyager had free-moving cameras, so they were snapping pictures of everything, and all of a sudden, one day it froze, and the bearings locked up. And like, what are we going to do? They couldn't take pictures of Saturn or the rings, and they said, well, it's pointing at Enceladus. Let's snap a picture. And this actually was from Cassini, but the Voyager picture is kind of faint and dark. It's hard to see, but what they found is something just like this. They found this little moon sitting inside the E-ring of Saturn, which is the outermost ring. It looks just like that. This is a real picture from NASA. It is called an occultation, where the sun is behind Saturn and it's illuminating everything. The E-ring is really diffuse and it's made of water ice. So they found this moon, Enceladus, sitting right in the thickest part, the densest part of this ring. And being scientists and using Occam's razor, they're like, that is not a coincidence. There's something happening there. So to cut to it, what actually they found out was that this little moon, this tiny little moon that's 313 miles in diameter, formed the E-ring. Think about that. That E-ring is gigantic. It is the second largest ring in the solar system. It was the first before they discovered one around Jupiter. As I mentioned, made of water ice. Somehow, this little planet, or this little moon, orbiting Saturn, has created this ring. And they're like, what's going on up there? To give you an idea how small this moon is, it could fit comfortably right next to Great Britain right there. So if it came and just landed on the Earth, that's what it would look like. Making sure not to crush Great Britain, of course. So here's how it started. Back in February of 2005, Cassini just decided, the Cassini team decided to send Cassini flying past Enceladus just to check things out, because they wanted to know, like, what's there, what's causing this E-ring thing, and what kind of readings can we find. So they turned on the magnetometer. The magnetometer registers readings from the magnetosphere of Saturn and so on. And this obviously isn't to scale. This is an artist rendering, of course. But this illustrates what they found. They found that the magnetosphere was bending around the south pole of the moon. And the only thing that would cause that is an atmosphere. And they looked at this and they said the data must be wrong. They all thought it was a dead icy ball. That's what they called all of Saturn's moons. And they saw that they didn't even think anything was going to happen with Enceladus. And in fact, they didn't even look at the data for, I think it was 28 hours after the readings came in. And they saw this and they said, this must be a mistake. So they scheduled 2 more flybys in the subsequent months. And they found out that indeed, this little moon has an atmosphere. And in March, I believe, of 2005, they published a paper and said, we have found an atmosphere on this tiny moon. And blew scientists' minds. They couldn't believe it. So just to cut to the chase, because I know it's really fun to get to the database stuff, this is what they discovered over the 20-year mission of Cassini with respect to Enceladus. It has a global ocean covered by an icy shell. There is a rocky core. That rocky core is being heated by tidal friction as it goes around Saturn and gets pulled by Dion and others. It gets squeezed and torqued, evidently heats up the rocks, and the temperatures of the ocean down at the bottom are the same as the temperatures of our ocean on the bottom. It spews out material. Cassini sensed that material. It found methane, CO2, molecular hydrogen, all the things needed for life. So basically, what the NASA team said, in a white paper, not in some link-bait article, they said, the readings from Cassini are a smoking gun for the presence of life. They literally said, smoking gun. And I read this in an article. I'm like, you've got to be kidding me. How do I not know about this? Oh, great. Yeah, I have to do a book and a video now, and I got to turn my attention now to Postgres. So that's what I'm going to do with you guys. So as I mentioned, I'm going to be telling this in a bit of a circular tale, because that's the way it is working with data. And I'm going to be repeating this again and again. This book and everything I'm doing, or everything I wrote, and also this talk, is about discovery of what's in the data, sleuthing the data, and also structuring it and putting things together. So let's get to, let's see, we're going to start with the discovery of the data in itself. So I went to the Cassini website, and I thought there's got to be some information here that I can download. I'm sure there's things there's like raw data there, I'm sure, that I can get. And as I was looking through this website, this is at saturn.jpl.nasa.gov, I was just overwhelmed with the amount of data, as I mentioned. It was just astonishing how much stuff there was, including all of the instrument data, the schedule information, everything, and I didn't even know where to start. And it shouldn't have surprised me. I don't know if anybody here has watched The Martian. I'm bringing it up again. But in the movie, there's a great scene where they found out that Watney is still alive. And Teddy, the director, said, well, we have 24 hours before we have to get this information out because it's public domain and we have to release it. So I found out that every bit of data that Cassini collected is available to all of us, and we can download and do whatever we wanted. And I thought, I'm just going to dive in from point A, just like an investigator would, if you've ever seen a show like The Wire or whatever, when they put the pictures up on the wall and they start stringing a bunch of string everywhere. I'm going to let the data tell me what the story is. That's what good investigation is. That's what good data analysis is when you start working with databases and trying to find things out. So that's precisely what I did. And I decided to find out where can I get a schedule, a calendar of events, commands, sents, and so on. Turns out the entire master schedule of the mission is available online, 61,874 rows of data. And you can grab this, and it's just a big, fat CSV. That's what it looks like. You have dates, you have the teams involved, the target like Saturn itself, the moon, Enceladus, or Dion, or Titan, and then a title and a bunch of other things. And I looked at this data, and I'm kind of a space nerd. So I saw, look at that linear mosaic of the Saturn magnetosphere. Doesn't that sound great? Methane band photometry. So I kind of sifted through all this, and I said, perfect, I'm ready to go. Now what I need to do is I need to take my investigator's hat off, put on my database administrator's hat, and I need to load this data into a database, Postgres. And I'm going to follow a process that data people are used to, ETL. Anybody heard of ETL? Extraction, transformation, and loading. The idea is when you're loading data into an analysis system, you go through 3 steps. The first is extraction, so you pull the data from whatever source you need to examine. So it could be bank accounts or whatever you're pulling into a data mart. You transform it so you can work with it. So you put data types on it, you put relationships in it, and do whatever you need to. You also clean it to make sure it's valid and good data. And then you load it into the database. That's it. It's a simple process. So what I decided to do is you can get by the way, you can get as complicated as you want with this process, or you can just be simple with it. You could just use Excel and kind of look line by line and fix things. Or in my case, I loaded it into Postgres, and I was going to do all the transformation in Postgres. To do that, I decided that I needed to create a schema, and that's what that first 2 lines are. I'm going to lock all of this raw data away into a schema, so I know that it's raw import data, and I'm not actually going to do anything with it. I'm then going to create a table, and this is really important when you're working with raw analysis data, is you just want to bring it in as absolutely raw as you can. Notice there's no primary key for this table. If I put a primary key on this table, then I'm influencing the data. In fact, if I even choose a primary key here, I'm also making a choice about the data, and that's me having some bias. And as silly as that sounds, it's critical when you're working with data and doing analysis that you do not change the raw source in any way. The next thing here is you'll notice that every single column is text. This is something I learned when I was writing the book, that Postgres stores text information or string values in the exact same way, regardless of data type. So if it's char or varchar, text, whatever, it's all stored in the exact same way. And you might be thinking, well, why is there no length definition on the column? It turns out you don't need it. In fact, you shouldn't put it on unless you absolutely have to have it. It's an extra hit when you insert data and do updates. Postgres has to do one more step to make sure that the data that you're adding to the database complies with the length. So the last thing I needed to do is to load it in. And you can load in a CSV into Postgres using the copy command, as you see here. And I'm just saying copy from this absolute path, pull in the CSV. Here's a delimiter. As you can see, the CSV has a header, so skip the first row, and then that's that. Now, one thing that a lot of people ask is, why are you using SQL to run an import? Why wouldn't you use a GUI? You can do a job, let's say, in some tool like pgadmin or Navicat. There's a ton of tools out there that can automate this process. And there's 2 reasons I'm doing this. One is idempotence, which is a word I absolutely hate. I don't know why, it's just one of those words that sticks in my head. Idempotence, as you might know, it just means I can rerun the same script over and over and over, and I get the same result. And that's critical. So I want to be able to do that. And it's easier to do with a script. You saw the script there. It was all of 12 lines or so. And I don't need to fiddle around with a GUI. Second reason is I wanted to keep this as real as possible. This is what database people do. They have P-SQL, Postgres DBAs have P-SQL, and they write their scripts, and they love their scripts. So I wanted to make sure that this was as real as it could possibly be. Next, and some people are probably going to throw something at me, but I like to use make. I don't know if anyone out there is familiar with make, but it's the Unix build tool. Its job description is that it turns one set of files into another. That's all it does. So when you compile things on a Unix platform, you just wire up make, call a compiler, it'll execute jobs, you orchestrate it. It's just like MS Build or any other build tool. The way that you can use it, dig that make file. The way you can use it with a database, this is how I like to do it. You have some variables at the top. You just tell it, here's the source files, here's where I want the build file to go, here's my database, and then execute the commands in a given order. I'm not going to dive too deep into this. I'll just tell you that this is all there is to it. What I have on disk, I have some SQL files, as you can see right there. I separate my individual commands out into individual SQL files. I load them in order. It gets concatenated and put all together into a build.sql file, and then I execute it, and that's that. Just run make, boom, it runs. So that's why I'm doing everything by SQL scripts. So, who here thinks that that worked? Just out of curiosity. Wouldn't be much fun if I asked. So what I needed to do, as I loaded the data in, and I went through and everything looked good, I needed to transform it, which is just a real simple step right here that simply means I needed to cast one of the string columns into a timestamp. That's my transformation, that's it. And then load it. And I was going to load it into an events table, because this is a schedule.events. That's the way that works out. So I ran this, and I had a really fun error happen. Keep in mind, this is data from JPL. This isn't just some random spreadsheet I found. This is from JPL. It found a leap year for 2014, and 2014 is not a leap year. Postgres, which is really good on these things, especially dates and times, barfed and said, no, that's not valid. And if you work with data long enough, you're going to figure that, or you're going to find out that dates are a massive, massive pain. So at this point, I have a choice. At this point, I can put on my DBA's hat and say, find another source for that date, or find some more data. Let's just move on. The investigator in me, the data analyst, is saying, wait, how did that get in there? And why is that in there? What does that mean for the rest of the data? Because if this is wrong, what else is wrong? So I can't move on until I answer that question, until I know more. Has anybody in here ever had to deal with a weird leap year date in a database? Just throw up your hands. Anyone? No one? Yes? Yeah. Does anybody in here know that Excel has a bug for leap years? This is true. This is, I would say it's hysterical, but it's really not. There's a bug that was intentionally built into Excel so that it considers 1900 a leap year. And the reason that they did this is because Lotus 123 had that bug. And when they released Excel, they were like, well, we need compatibility with Lotus 123 database stuff, or spreadsheet stuff, so we're going to have the same bug too. Why not? We'll make it a party. So that's in there. And so as an analyst, I'm feeling like this has got to be it, because I'm dealing with a spreadsheet, right? So, and it's messing up dates. And right here, I'm sensing there's something. I sat down and tried to do the math and tried to figure this out, and I couldn't quite do it. I couldn't make it match up. But I did look online, and a lot of people said, oh yeah, 2014 is a weird ripple effect of this. So I just took their word at it. This led me to build a story about how this got in here, and this is my best guess. So here's the offending dates right there. And over here on the far left side, you see we have a column called start time UTC. That start time UTC is formatted in what they call PDS compliant date format, or planetary data services date format. It's just year and then day of the year. And so scientific instruments that are up on Cassini, this is how they record the date. So someone somewhere said, that's not readable, I don't know what that is. I'll add a column and I'll name it date. And so they put it over there and they said, well, let's try and read it. So they tried to apply Excel's formatting to it, because that's a very Excel-looking format, don't you think? And it puked. And what I'm thinking is, this is my guess, I don't know if this is the answer, but what I'm thinking is that it was a really old version of Excel, maybe running on WinXP or something like that. So I'm feeling good about this. I'm feeling like I can close the door on this. I've got a different source for the date. We can move forward. But overall, this is something that, again, you think about when you're working with data all the time, and this is kind of a mandate of mine. People and data just do not mix. If human hands figuratively touch data, it's suspect, always. People do horrible things with spreadsheets. They really, really do. The good news is it's easy to fix. I didn't have to do any additional parsing to get Postgres to read that text column formatted in the PDS compliant format. It just understood it. And as I mentioned, Postgres is really, really good about dates. OK, so moving a little bit ahead, this right here is the data that I was able to pull in, and I queried it to make sure that everything looked the way I expected it to. And the reason I wanted to pull this up is this is the data from the flyby of February of 2005, the very first one, flyby of Enceladus. And right there, the closest approach observation, they turned on the magnetometer, they took a look at the thermal stuff, and they kind of just poked around. What's out here? This right here changed everything in terms of planetary data science. This flipped the Cassini mission on its head. This is the start of I'm not exaggerating. This is the start of destroying people's careers. From this point right here, they actually decided to do 20 more flybys of Enceladus. And they took that time from other teams' time on Titan and other moons out there, and other observations of the rings and so on. There was massive fights inside of the Cassini team, and people quit, people moved on, people yelled at each other, and I read a great article about this. They said the drama between scientists is nothing to be trifled with. So I just thought that was interesting, just looking at the data right there, marking that moment. Okay, so in this book, I have a main character. This is a fictional narrative book. That's the only way I could really tell the story. It's a fictional narrative wrapped around this process of discovery of the data of Enceladus, and the main character's name is Dee Yan. And Dee has to load up some data because I, as the CTO of my fictional aerospace company, Red 4, am going off to JPL in Pasadena, and I'm trying to pitch so we can have our probe up on the next Cassini mission. And I can't work with the data, so I need her to step in. So she's got 3 tasks. Task number 1 is flybys. Task 2 is going to be looking at the speed data, and then task 3 is going to be playing around with some chemistry. So Dee's first task is to find out when the exact flybys happen. So there's 22 total flybys. She needs to find out down to the millisecond or the microsecond when were these flybys, because we need to know so we can have an analysis window. I'll get to that later on. So the first thing to do is to look at the schedule. And what if we just do a fuzzy search on the term closest approach? We just saw it. Why not? And there's timestamps associated with the data. We know that. We run this query. We have 25 rows. And I just said there's 22 flybys, so why would we have 25 rows? That doesn't make any sense. So this means we need to do some investigation again. Take off our DBA hat, put on our investigator's hat, and we can take a look now at those dates associated with closest approach. And you can see that on November 2nd, 2009, there was somehow 2 closest approaches, which doesn't make any sense. The reason why it doesn't make any sense is because Cassini flies very, very fast. Does anybody know how fast Cassini would fly by this moon at full speed, or at flyby speed, I should say? Anybody have any guesses? Does anybody know? There's science nerds out here, I know. 19,000 miles an hour. That's how fast it goes by this thing. So the idea that it could fly by, turn around, and come back won't happen. In fact, the only way that it could turn around is to go and then circle around Titan. It's another stupid little bit of trivia. Titan actually drove Cassini around the Saturnian system most of the time. It was called the engine of the mission. That's the only way it could go out and come back. That would mean for it to even be able to do 2, it'd have to go into orbit. And so I ran a little query because I thought, why not? And this is how fast Cassini would have to be in orbit, 19 orbits per hour. So that obviously is not realistic. It would have to be about a foot off the surface. So we can basically say that that data isn't going to work for us. So what if we change the term? Instead of closest approach, what if we use the term flyby? And we're querying on the title. One more time, we're doing a case-insensitive search on the term flyby. And I don't know if it's 1 word or 2, so I'm just doing an or statement here. And I'm doing an I-like, which is a case-insensitive like. Here's the results for that, and that's run over the entire data set. And this shows me something else. At the very top there, you can see there's 3 Titan flybys. There's T0. Down below, you can see T3, T4, and T5. The casing on this flyby is uppercase, whereas other flybys are lowercase. And then we also have TA and TB, which don't follow any coherent naming scheme. So I can't use any regex, blah, 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 blah. What this is telling me overall is this data's got problems. We have inconsistent flyby names, we have duplication, we have leap year weirdness, and then we have misspellings. So what I'm starting to see as a data analyst, if I put my analyst hat back on, is that people, we hate people. People put this data set together. They put this spreadsheet together, probably just sat there and typed it in, and maybe had autocorrect, or not autocorrect, but the autofill, fill in the rest of the thing. What that basically means is we can't trust this data source, so we actually have to try again. We have to think, well, okay, where can we find some data that's going to work for us? We can't trust people, so what about instruments? Because Cassini had 12 of them. And it turns out that we have 2 instruments that track data, a lot of data, actually over the course of the mission. We have the CDA, which is the Cosmic Dust Analyzer. That's rad. It's a mass spectrometer. And then we also have the INMS, which is the Ion Neutral Mass Spectrometer. Basically, they both collect space dust. One of them pulverizes it, and the other one zaps it with electrons. And they try and take a look at the chemical constituents of the data. And they track where they were, how fast they were going, and the date. This is the data for the IMS. I downloaded it and dropped it on my machine. You can do the same thing if you want. This is 30 gigs of data. You can see the way they separate it all out by year, and then month, and then day, and then a bunch of 2 megabyte spreadsheets. If you take a look at the spreadsheet, you can see there's a ton of crazy data in there. This is good. This makes me happy. If I put my analyst hat back on, this looks like a machine recorded all of this, and that's what I want to see, because machines are a little bit more reliable at tracking data than people are. So looking this data over, I'm quite happy. The other thing that comes with this data is a manifest. It tells you exactly what the data should be, and then it also tells you what format it should be in. In this case, I want to make sure there's altitude data in there, because if I know the altitude as Cassini flew by Enceladus, then I should be able to figure out when it was closest to Enceladus, and I can use that timestamp to figure out the exact moment of the closest flyby. So here's the catch. The IMS records data every 30 milliseconds. So it records altitude, timestamp data, chemical readings, and so on, every 30 milliseconds. That's really fast. So even going at 19,000 miles an hour, you're going to end up with data that looks like this. This is the lowest point observation for the October 10th, 2008 flyby, the lowest it ever went, 28 kilometers above the surface. I believe it was flying at 19,000 miles an hour again. They got so close, they hit the plume at full speed, caused the thing to rotate and almost tumble and crash into Enceladus. And they realized, uh-oh, we're getting a little too happy with this. So, but this presents a problem. Which timestamp do you take? And as a DBA, I'm saying, I don't care, just take a dang timestamp. We need to move on. You're wasting time. As the investigator, I say, well, no, we have to know the exact moment of the lowest approach. So there's a lot of hedging you can do here, but the obvious solution, at least to me, is to take both dates, take the minimum and the maximum, cut it right in half into the median, and then take that timestamp, and you're good to go. That should be your closest approach. And in fact, that is the data that I ended up with. The problem that I had was that I needed to be able to group those low flybys by something. So I thought, well, flybys happen, really quickly, so we should be able to group by day. Turns out that some of the flybys happened right at the stroke of midnight, so you end up with flybys that actually span 2 days. That doesn't work with a group by. So what I decided to do, just to cut to the chase, is write a big, crazy query that looks like that, and I grouped by week instead of by day, and I was able to capture what I have seen to be the most precise flyby times that's available. And that's them right there. And I have 22 rows, so it looks good to me. And I have altitude data and timestamps, which means victory. And I was very excited. The query on the left here, I'm not going to talk too much about, but I do want to point out that this is what's called a common table expression. In Postgres, this is actually 2 queries in one, or 3 queries, I should say. Postgres and other databases, SQL Server and other databases do this, but Postgres has the most complete implementation. You can basically say with, give it a name, and then say as, and then you can wrap a select statement. That's what I have at the very, very top. And you can pass the results of that into the second select statement down below. So this is kind of like piping in functional languages, is piping one thing to the next, and then down at the very bottom, you just select your final result. CTEs are amazing, and a good friend of mine told me once that they are the most underused bit of functionality in any database, and I completely agree. So we now have timestamps. That is an exciting thing. Now we can move on to our next task, which is to find the speed data. So there's 2 ways to do this. You can go the easy way, or we can go the hard way. And so always want to start with the easy way, because why make things hard if it doesn't need to be hard? I can just go to the Cassini website. It's up at, again, saturn.jpl.nasa.gov. And if I take a look down there at the bottom, I can see there's altitude data and there's also speed data. So that's what I started doing. I just went through every single flyby, which is up here at the NASA site, and I just created a table and I just kind of wrote it in by hand. The problem with doing this is that websites are made by people. So there's no way in my mind as a data analyst, putting my analyst hat back on, there's no way that an error did not make its way into that web page. I don't care how good you are. When you're talking about scientific data as accurate as it needs to be. So case in point, there are 4 total problems on this page. I've highlighted 2. First is the name, Enceladus 1 flyby. That doesn't actually exist. There's no flyby with that name, but for some reason they chose to put that up there. The flyby's name is actually E-1. Not that that matters, but to a data analyst person, it kind of does. Second bit of problem is, for some reason, there's no altitude data and there's no speed data. For no reason. It's in the data set. They just decided not to put it up there. But there's two other problems. Take a look at this. This is one of the cool things about working with data is you start to develop a nose like a detective will. When they hear an inconsistency in a story, they jump on it because they know that that's the weak part. And looking at the data here, there are two other inconsistencies. Does anybody see them? Yeah, that's right. The date. For some reason, the date here says March 8th, but the flyby is on March 9th. That's a problem. If we take a look at the data that we just collected, you can see on March 9th, 2005 at the very, very top there, March 9th on the image, March 8th at the top of the page. Can anybody guess why that might be? Why would there be a discrepancy where it's later in UTC? That's right, later in UTC time, and then Pasadena is in Pacific time. Well, it turns out that's not actually the problem. The problem, I actually tried to find this out because the discrepancy in dates between what JPL has versus what's in the data that I looked up from the IMS is 9.2 hours. Just to dive into this for a second, I think the problem is actually back to that Excel spreadsheet. Because if you had a leap year, you add a day to every single thing that comes beyond that. So that's my theory. I have no idea. So there's one other discrepancy up here. I don't know if anybody could see it. I saw it, and I just couldn't believe it. So what does this tell you? To me, it tells me someone grabbed a random image, opened up an image editor, and just started typing information on a thing and thought, well, I don't know, we'll call it E04, even though it's E1. So I don't know what the deal is with that. Point is, do I have any Warcraft players, any WoW players out there? Horde? No? All right, sorry. Trust no one, especially yourself. And what I mean by that is, as you start looking at the data, and I'll come back around to this, as you start working with data, you start to build a story in your own head, because as people, we want stuff to make sense. So we're going to try and link things together, and sometimes the story is shouting at us, saying it's not, that's not really happening, but we chose to see one thing. So that bias works its way in, and we'll see that later on. I think I was talking about speeds, so let's see if we can get back to figuring out speed information. Turns out that the IMS records speeds in 3 different ways. It needs to know those speeds because as it's cruising through really fast space, it pulls in these particles, and the speed of those particles hitting the instrument actually will offset a few things, and so they need to be able to do some back calculations to figure it out. So they have 3 ways of tracking velocity. The first way is by tracking velocity relative to Saturn itself, in what they call the Saturn coordinate system. That's what that is on the far left side. The other is tracking it relative to Enceladus, or the target, and the third way is tracking it relative to the ship itself. So the two on the right side, I could just pick one and I could use that to find the actual speed relative to Enceladus. That's what I want to see. The other one that you don't see up there too, they also track speed relative to the sun. And it kind of gets weird when you start trying to figure out speed data and you're like, speed relative to what? The next issue we have is, and we're going to dive into a little math, velocity is a vector. So when you're talking about velocity relative to something, you have to consider that it's a vector, and a vector is a line with a value attached to it. So the only way they're going to track vectors in anything reasonable is to do it along a coordinate system. And so this is a ship relative coordinate system in the X, Y, and Z space. So that's how fast it was going in each one of those directions. So we're going to talk about skiers running over lugers just for a quick second. If I wanted to know how fast that luger is going down the hill, aside from just reading the label I put up there, if I only knew the X and Y coordinates, does anybody here know how I could actually figure out the speed of that vector going at an angle between the X and Y coordinates? Well, it's a right triangle. So a squared plus b squared equals c squared, Pythagorean theorem. I should be able to use c squared, or square root of c, and whatever that equation is, and then I can figure out the speed. Turns out you can do the same thing in 3 dimensions. So we can do it in 2 dimensions, we can do it in 3. We have x, y, and z is coming out at you right there at the bottom corner. This is the Pythagorean theorem, just in case you forgot like I did. And then this is the way you could apply it in 3 dimensions. So that was simple to figure out, and I could plug that back into SQL, and I made a function in Postgres called Pythag. And in here I'm taking in 3 values, x, y, and z. And then I just need to take the square root, as you see, and I'm able to use this now with the raw data from the IMS. So these are the 3 columns that I was just talking about, x, y, and z coordinates for velocity, and this should give me precise speed data. And here's the fun thing, it actually worked. So this is the data in the center column there where it says speed. That's the data that I actually grabbed from NASA's website. And I loaded it into the table, and I named all the flybys. This is my flybys table, by the way. And then I compared it with my calculations, and would you know, it is exactly the same. As a matter of fact, I was able to calculate the missing velocity data for the first 2 flybys. So I'm thinking that I could do a pull request. What do you think? JPL, take my pull request for this data? Okay, I have altitude data, I have speed data. I now should be able to do some really interesting chemical analysis. So my fictional aerospace company has a fictional analytics team. And what they put together was an analysis window. The reason they did this is because they figure that the plumes that are being pushed out of the South Pole emanate from the center. So there's heat in the center of the moon, and it basically pushes out the plumes, and the plumes radiate out in a 34-degree angle. And I completely made that up because I can, so why not? So what I want to track here, and that's my great rendering of Cassini, I want to track when Cassini enters this area and leaves it. And now that I have speed data, which is telling me time relative stuff, I have speed data and altitude data, I can figure this out. And so in the book, that's precisely what Dee does. And now she can do chemical analysis right at the beginning and end of that window. To do the chemical analysis, we need to be able to figure out what the IMS is telling us. So it's recorded all kinds of interesting information. I'm not going to dive too deeply into that. And we have a lookup table that comes with the data. And that lookup table is, as you see here, chem data. It's got the name and the formula, molecular weight, the peak. The peak is the thing we want to see, and sensitivity, which we're not using. The thing that I am specifically looking for is the smoking gun, as they called it in the NASA paper. The smoking gun is the chemical signature of the plume material. If they find molecular hydrogen, carbon dioxide, methane, and water, they're going to find evidence of a bioreactor. This is fascinating stuff. There are these black and white smokers, and some of you, probably all of you know this, these black and white smokers that are in deep sea trenches on the Earth here. And they basically spew out this highly toxic, very warm, mineral-rich material that you can see right there. And there's little bits of microbes that actually feed off of this stuff. And they feed on the molecular hydrogen. And then they give off methane and carbon monoxide and carbon dioxide. That interaction right there causes a whole ecosystem to form where you get these worms and all these weird wacko things. You can see them there. These systems are 100% cut off from the sun. And until 1970, that was the feeling from biologists, that life on Earth was powered by the sun. It's the result of the sun. Everything that happens here, they figured, well, is powered photosynthesis in the sun. But this came along, and they said, this is an alien world on our planet, right here. It just kind of appeared out of no influence from the surface at all. So taking just a philosophical step back, makes you want to question life itself. And where does life come from? Is it random? Is it highly unique, as a lot of people have thought? Or is it just normal? I mean, is it everywhere? And you consider that life popped up in the bottom of the ocean from no influence from anywhere else other than having these materials, water, chemistry, and heat. Those are the 3 things for the bioreactor. It kind of makes you wonder, we've just started looking for life somewhere else, and we have seen the signs in Enceladus. We've actually seen the life here. Is it everywhere? And in fact, a lot of people are taking this up. And just really quickly, I wanted to point out that a lot of people are doing these research papers musing on just that. And they call them, as I mentioned, bioreactors or origin of life reactors. Okay, back to Cassini. The problem that we have is that Cassini doesn't have any instruments to tell us if life exists. In fact, I have a whole argument in the book whether it would even matter if it had a camera and it could somehow go below the ice and snap a picture and confirm that there's life. Would anybody believe it, number 1? And 2, would anybody care? So I don't have an answer to that. I mean, I think Star Trek nerds like me that grew up in the 60s and 70s feeling optimistic about the world and, we're all moving to space at some point, it matters to me. but I know a lot of folks these days have different opportunities they have to deal with, and I don't know, maybe they would care, maybe they wouldn't. So we come around now to actually doing the analysis on the data, and this is the query right here. To me, this query is probably the most important query that you can run over the entire Cassini data set. This is the culmination of the entire mission with respect to Enceladus. And I want to step through this query because there's a lot going on. The very first thing is I mentioned I have a flybys table, so I just want to pull information from that flybys table. It's got date, time, speed, and altitude information. The second thing is I want to have the chemical data name, and then I want to have the source. And the source simply is how the IMS collected the data from space. There's two ways it can do it. It can just open up its chamber and take the stuff directly in from space, from the plumes. The other way that it does it is it has a little vacuum chamber where it just lets the data, or lets the plume material seep in. The reason they have those two ways of doing it is the closed source is what it's called, with the vacuum in the chamber, is good for lighter chemicals and picking up things like that. The open source is good for picking up heavier stuff that can collide with it and remain intact. This is important because the closed source stuff reacts with the chamber, and when it gets in there, sometimes it'll just volatilize and it'll give off hydrogen, so you get false hits. And also, just so happens that Cassini's exhaust is heavily laden with hydrogen because it's hydrazine, among other things. So that causes problems. So NASA figured, well, if we can open up the open source and try and detect hydrogen, we'll have something. We'll talk more about that in a second. Finally, I'm going to link on the peak in the chem data. I'm going to link on the peak and the mass per charge that is returned from the IMS. And all this simply is when the material enters the mass spectrometer, it is zapped with some electrons, and then it's energized, and they go off and they bend in a particular pattern. It's the same thing as when you're looking at the sun reflected through some sprinklers, and it bends it into a rainbow. That's a spectra that's given off. And the same principle applies with electrons blasting this material. So what you want to find is how energized is it? And so you can get that from the mass per charge, and you can link that over on peak. That is in a unit, in case you're curious, called Daltons. And then finally, we're just looking for the formulas. Molecular hydrogen, methane, CO2, H2O, and off we go. So to me, this query comes down to, are we alone? And I know that sounds a little bit romantic, but I think, well, I'll get to this in a second. I think if the clues are there, it tells us something. And being an investigator, we want to see the clues. So here's the results. This is fascinating to me. This is from the E21 flyby. This is when they opened up the open source chamber wide open to collect the plume material. It's the one way they could be sure that they could detect molecular hydrogen that was almost guaranteed to be external to Cassini itself. You can see that the hit down below is from the OSNB source, which is open source, and we have a lot of it. If you look at the very top, water, that's what's expected from the plumes. Methane is number 2. That's what is excreted by these little microbes when they take in the molecular hydrogen. We have carbon monoxide, and then we have a bunch of other organic compounds. That is the smoking gun that the team is referring to. And this little moon, I love this graphic, I just have to show it one more time. This little moon now is being regarded as subject number 1 for the next probe that we send up. And right now NASA is actually putting together what's the word I'm looking for? They're calling out for bids for the next mission to go back up, and they're going straight to Enceladus. And they already have the instrument made. It's called SELFI, believe it or not. Search for Enceladus life, something or other. But this will have the ability to go and take a look at the biological material, if any, under the ice in Enceladus. So to put this in perspective, a lot of people ask me, do you really think there's life up there? How likely is it? And what I do is I try and reconcile the chemical data with something that, looking at this picture here, let's say I asked you, are there people inside this cabin? And we can see footprints walking all around. We can see lights on inside, that ladder. There's probably a car parked over there. We just can't see the people. We might see smoke coming out of the chimney as well. This is the level of evidence that we have right now for Enceladus. We just haven't taken a picture of the little microbes, which I think is absolutely fascinating. So as I mentioned, I wrote a book about all this, and I thought it'd be kind of fun to, as you could tell, dive into the subject matter while also learning Postgres and learning about data. That's it for me. If you guys have any questions, please do shout it out. Any questions?
Has NASA already done that same sort of work?
Say it one more time.
Have NASA already done that same sort of analysis on their data?
The question was, has NASA done this type of analysis on the data? And yes. Not like I did, because I did it more for just kind of playing around with Postgres in a database, but there still are so many white papers coming out. They're still trying to figure out, which I touched on briefly, but they're still trying to figure out where this heat's coming from. Because the heat that's coming from that moon is, I think, 20 times what it should be. Even with the tidal friction model, it doesn't account for it. So they don't know. That plus radioactive decay doesn't cut it. They have no idea where the heat's coming from. But there are lots of theories coming out, which is really nuts. So, yeah, you had your hand up back there.
Yeah, do you know what this SELFI thing's going to do? How they're going to get a camera in there to actually look?
Yeah, that's a good question. The question is, do I know what SELFI is going to do? Is that it? Yeah, I don't know. My feeling is that it's not going to land. I don't think it's going to land. I mean, the only thing it could do is to land, hit the ice, put it, because there's no gravity there pretty much. They'd have to drill in and then melt their way through the ice and then wire a camera to go down all the way to the core. That's a lot of wire because it's salt water, so it doesn't transmit any radio signals. That's an expensive mission. It's not going to do that. I know it's a sensor and it's super highly sensitive. So I think what they're banking on, if I can go back to this slide here, what they're banking on is that there is so much material being spewed out into space. It's awesome. I mean, this thing is like, here's your sample material in my ocean. Just come and sample it. So I think they found sand particles in there, and I think what the reasoning is they should be able to find microbes as well, which I don't know, maybe. Yeah. Anyone else have a question? Yes. Oh.
A few slides ago when you had the one with speeds,
Yeah.
you've been going on about 22 flybys, but there's 23 records.
Yeah, I didn't talk about that too much. 23. Let me go all the way back. Oh, that's interesting, isn't it? No, there's a reason for that, and I can't remember what it is. So I got the count wrong, right? Okay, so here's the problem, right? So I said 22 total flybys because NASA calls them E1 through E22. They didn't count the first one. E0 is my name. So the first one was just to go snap pictures. It wasn't necessarily this scientific investigation, so it didn't have a name. So when you look it up online, it's really confusing. It says E1 through E22. And so there's actually 23 total flybys. Thanks. That's a great correction. Yeah?
You said that the data lead the story. Any other curiosities or intriguing things?
The question is, I let the data lead the story. Were there any other curiosities? Yes. There's so many inconsistencies, and that's the thing that always kind of locks you on. Like, why is it like that? Primarily, I hate to sound conspiratorial, but why haven't we heard about this? You know, why isn't this more widely known? I mean, people, when you talk about life, possibilities of alien life, everyone's like, well, Europa, Titan, you know, these are the focuses. But this has way more. We have the data because it's throwing it out into space, and we've registered it. We know it's there. And so that, to me, is a weird inconsistency, that why don't we know more about it? And so that, I think, is one. But in terms of the raw data itself, it's just not jumping to mind. But I found a bunch. I have a bunch of notes, but I had to keep on the straight and narrow. And if I remember, I'll come find you. I don't have it on the tip of my tongue. Anybody else? All right, well, thank you so much. Appreciate your time.